Now let's talk about proportional control. This is a little bit more nuanced. So in proportional control, this is a closed loop controller where the plant or the system that we're working with has some variability, has an analog sort of input to the system. So the control variable can take lots of different states, or is a continuous state rather than a discrete state. It's basically in proportional control, it's the simplest possible continuous controller where our control signal is proportional to the error. The way we calculate error is we take our set point, whatever our desired position or variable in the system is, whatever we want to control, whatever our desired target is, and we subtract the process variable or whatever the current state of the system is. So we're looking for the difference between our goal and what we have actually measured. This gives us the error, and our control variable, whatever it is we're inputting into the plant, the U would be right here, is some constant, this constant K sub P. K sub P is our proportional control constant multiplied by the error. This is very straightforward, right? This is basically saying I want, based on how far off I am, I want to increase my control variable if I have a positive error, and I want to decrease my control variable if I have a negative error. I've overshot if I have a negative error because my measured value is bigger than my target, so I've overshot. I want to decrease the signal that I'm putting in. If I've undershot, I have a positive error because my target is above my measured variable, so I want to increase the control variable, whatever it is I'm putting in. You can think of it as speed for the system. So if I'm trying to hit 60 miles an hour and I'm at 30, I have an error of 30 miles per hour. So I want to increase the pressure on the accelerator to make sure that I hit my target. Also, if I'm going too fast, I want to decrease my speed. My error will be negative, right? Because I'm going too fast. I want to release the gas a little bit. I want to decrease my control variable so that I slow down. Another example is the steering on our cars. If if I have a specific heading that I want to reach, then I can calculate my error heading as my desired heading minus my reference, my target. So my error heading off of the reference is, if it's less than 0, I want to wrap around to the other side. Basically, I'm trying to figure out if which side of the angles I want to go. If it's too far to the left, I'm just going to make it straight up. My steering angle is 90 minus my heading. So if I'm between 45 and 0, I want to make it proportional to 90 off of my error heading. So I want to hit that target. If it's less than 180, then I'm just going to slam it all the way to the left and hope for the best. If it's greater than 315, which is the other side because my heading is straight ahead, then I want to make it proportional to something in here, right? So what would happen is if I'm too far away, if my heading is way over here, I'm just going to turn as hard as I can to get in that direction. And then when I get closer, I have a little more nuance to steer in the right direction. Same thing if I'm going too far off the other side, I'm going to turn that way as hard as I can until I get within range. Then I'm going to slowly come in line with the rest of them, right? In this case, you don't see a constant in here. This is directly proportional because we're still all in the same units. So my error heading is in degrees, my control variable, my steering angle is in degrees. That way they both agree. The constant is basically there to serve as a unit conversion between the system that you're controlling, the input variable that you have, and the variable that you have that you are controlling. And that can get you in the ballpark, but you also want to dampen it down a little bit. And we'll talk about the response patterns when we get to the next unit. So let's look at another example. So here we have a speed control example. I have a simulated car on a simulated road, and I can see right now my control signal, my accelerator signal, is input at 50 out of 100. So I am right at my sort of maxima. I have a constant amount of pressure on the vehicle itself, right, on the accelerator. My speed is currently 60, but my set point is 30. So my error is 30. I want to slow down a little bit, right? So let's write a controller that does this. So my control variable is the percent out of between 0 and 1 of my accelerator pressure. So that's what I want to calculate here. So my level should be equal to some constant, which is my KP, so I'm going to call KP, times my error, which is going to be remember, the set point minus my measured value, right? And that's the basics here. We're going to need KP, so let's set another float at KP, and let's just set this equal to 0.1 for now to see how it does, right? So let's see what happens when we do this. So here we are, where my set point is 30. My actual speed in this case is 27.92. Now if I, which is pretty good, right? So here my error is really low. It's steady state at 23 or 2.3 miles per hour. And that's because there's a little translation in the system that's not totally perfect. And this is a problem with proportional controllers, is that they will converge to a point and they won't get all the way there. And we'll see in the next unit about how to bridge that gap. Let's see how this performs under some changing conditions. So let's increase my set point to let's increase it to 60 miles an hour. And you can see the control system slammed on the gas pedal. It accelerated up to a steady state threshold and then stopped. So we had a increase in error, and then the error started to drop, and we're back at our speed. Let's go really fast. Again, we accelerated up. We reached got really close. We're at 83.7, and our steady state error is about 7. So this is the example we have here for how a proportional controller is really simple, and it can get us most of the way to controlling a variable in a system very easily.